An infinite impulse response filter is a type of recursive digital filter. The characteristic that it has an internal feedback loop unlike the FIR filter. This means that to calculate the current output, the filter will obviously use the current and the past input samples, but it will also use the previous output samples. That means the filter's output at any point will have a component or a part of the previous output. So if you give it an impulse, so the impulse will continue to generate output, because every time the output that is generated, it will be a part of that impulse. For example, if I take a physical example, like if you clap in a room, so the walls will echo your clap. First you will hear the initial loud clap. So when you give the impulse, that is your clap, you will hear the initial loud clap, but a moment later you will hear an echo of that clap that is much quieter. A moment after that you will hear even a more quieter echo, and this continues until the echo will become progressively quieter. That is how the basically IIR filter will work. For example, then you can give an input of maybe say 10. So at time is equal to 0, the input will be 10 plus a portion of the previous output. But since before time 0, that is previously past the impulse, there is no output generated, so it will be 0. So initially the output at time it equal to 0 is 10, but since it is an impulse, there will be no input there will only be an initial input at time is equal to 0, but after that the input will be 0, but the output will not be 0, it will be a portion of the previous input. So now at time equal to 1, the output will be say maybe 0.9 of the previous output, which was 10, so it will be 9. Then again it will be 0.9 of 9, which will be approximately 8.1, and so on. So the output will continue to fade away slowly, and in theoretical it will continue to fade away till infinity. It will never be 0, it will always be there. That is why it is called a infinite impulse response, as you are getting a constant infinite output for a given input impulse. Now I told you that the infinite impulse response filter is a type of recursive digital filter. I explained about the recursive nature being its feedback loop. So the filter's current output will always be calculated by the current and past input samples, but also its own previous output samples. Now that is represented by this difference equation that you can see. Now here the yn is the current output sample that is at a specific moment in time n. Now the first of all this equation is derived. First we take the transfer function of the filter in the analog domain, then we operate a bilinear transform to convert it into the digital domain, and then further if you do, you will get this equation further calculation. Now the first part that you can see, that is summation from I equal to 0 to p bi x of n minus I, that is the input terms. These represent the input terms, that is the current input and the past input values. So xn will be the current input, then xn minus 1 will be the previous one, xn minus 2 will be that previous. So it takes into consideration all the previous input values. Okay, now the bi term is the gain. So the equation that I told you that you get in the z domain, the numerator of that will be the gain of the filter, that is simply a multiplier. Okay, now the second term is much important, related to stability of the filter. Now if you see, Now the second, as I told you, the second part, the EJ that you see, it is the pole location of the denominator of the equation that I told you that you obtain in the Z plane. So now if the value is greater than 1, the filter would be unstable because it will continuously keep increasing the output. For example, the impulse, if I take the example of an impulse input at time 0, so at time 0 the total output will be at 10 because there is no previous output, so the total output will be 10. Now at time equal to 1, the input will be 0, right? But if the term is, the pole location is outside the unit circle, that is above 1, say AJ is 1.1, then it will be 1.1 into the previous output that was 10 at time equal to 0, and it will be 11. So continuously the output would be increasing and the filter would become unstable. So it is, so in filter design, it is, we need to ensure that the pole location is inside this unit circle so that we get a controlled output and the system remains stable.
I will be explaining you the hardware implementation for IIR filter. We have used STM32F411RE Nucleo board, and I'm using the STM32Cube IDE. You can see that this is the basic code that I've used. Delay.c and UR.c have been directly taken out from the datasheets. For UR.c, I have enabled clock access to UART2 through APB1 ENR and AHB1 ENR. I've configured my alternate function register and my motor register according to my alternate function pins. Then I've configured my baud rate register so that my system works at 16 megahertz. Then the control register 1 for my transmitter pin to work perfectly, which is on pin 13. Your dot write and input put character have been directly taken from the standard C library, for which I have included two files, system calls and system memory.c, which is available on the internet. For my filtering code, specifically to initialize my filter, I've used a function. In this, the alpha is the smoothing factor. The smoothing factor should always lie between 0 to 1. We have taken the smoothing factor to be 0.8. I've used a basic if else statement so that my alpha or my smoothing factor stays in the range. To calculate the output, I've made another function, and this is the main function, filter.out. This is the line in which the whole code runs. You can see that there's a filter dot out over here and a filter dot out here as well, which clearly indicates this is a feedback loop. In a feedback loop in my code, the system is taking input of the previous values and output of the previous values as well in order to calculate the output of the present value. When it comes to my main.c file, I've included all the .h files required. Enable my FPU. FPU needs to be enabled because it's the co-processor access control register through the system control block, which kind of needs to be configured. This is a systic init wherein I've configured it to 16 megahertz. For my main while loop, for the input signal, basically I've taken a base signal, which is a hypothetical signal. You can either use a sensor in this place. Because we do not have a genuine sensor, we are making a hypothetical input which will get filtered. This is the base signal which goes from 0.5 to 1, and I've used the random function which randomly takes the code from 0.5 plus and minus 0.5 from 0.5. It's a random generator. Then I've incremented my counter, and this I've printed my values. let me build. It's built perfectly. Let's run this. You can see that the code is running. Yes, works perfectly. Then we go to device manager and see what port. Yes, perfectly. ST link is connected to COM4. Then we'll go to PuTTY, which is a serial monitor. Get COM4. My baud rate is 115200. We go to terminal, all session outputs. We'll name it SNS mini project dot log, and we can clearly see the output. What's this? Now this file is successfully saved. Embedded PuTTY SNS mini project. I'll cut off the first few lines, okay, and save it. Then I'll go to an Excel sheet. Import my data. Yeah, from text and CSV files. Go to new volume D. And SNS mini project import. So we'll load my data. Okay, now my data is loaded. Now I'll plot the graph, for which I'll go to insert and take this graph specifically, the line, and you can see that a graph has directly been made. Column 1 shows, which is the blue lines, which is my input signal, and column 2 the orange line, which is my output filtered signal. This clearly shows that our code is working perfectly. Thank you so much.
Has an advantage that the IIR filter is very computationally effective because the coefficients that it uses, the coefficients that I told you about BJ and AJ, to create an echo that is continuously feeding, it would use only those two coefficients to create that, because every time the output that is generated, it will only be a part of the input. It is the great advantage of the feedback loop that we can efficiently get the output without any computational cost, unlike the FIR filters that will require more coefficients to do the same job, because there is no feedback loop there and we have to rely only on the basis of the inputs that we have given. But the advantage, as I told you, is that it has no signal distortion, but yes, it is computationally more expensive to do. The biggest drawback of the IIR filter in terms of a FIR filter is that it will not delay all frequencies by the exact same amount of time. An IIR filter has a non-linear phase. If I give you an analogy, then if you play a musical chord that is played of many frequencies, then what will the FIR do? It will delay all the frequencies of that chord by the same amount. So you will hear the same chord but just a delayed version of it. But if you compare that to a IIR filter, it would, you know, it would delay some frequencies more than the others. So you will hear the different frequencies of the same chord at different intervals of time. So this distortion actually makes IIR filters unsuitable for applications where exact shape of the signal is critical.
So now that we've seen how our IIR filtering system works, let's see about where it's actually used and why it's still so important today. You must be wondering, what makes these filters so special? And I have the answer. The thing is that they produce a strong filtering effect using very few coefficients. In simple terms, they are powerful, they're fast, and efficient, which is why they are used almost everywhere signals need cleaning or shaping. In audio processing, IIR filters remove background noise, improve clarity, and create effects like equalization. In communication systems, they are used to eliminate unwanted frequencies, reduce distortion, and recover transmitted data accurately. In biomedical devices like ECG or EEG monitors, they help remove interference and make signals easier to analyze. You'll also find them in control systems, image processing, smartphones, and even IoT devices. Anywhere real-time signal processing matters. Now, speaking about their future relevance, as our technology keeps moving towards faster, smarter, and smaller devices, IIR filters are becoming even more valuable. Because they require fewer computations than FIR filters, they save energy and work great on low power systems like wearables, edge processors, and embedded systems. And with modern DSP chips and improved stability design methods, IIR filters are now more reliable and precise than ever. So, in short, IIR filters may be simple in concept, but they quietly power a huge part of our digital world. From the sound in your earphones to data in your smartwatch, they help keep everything clean, clear, and efficient. That's why they'll continue to be a key part of future technology.